I'd like to now welcome and invite Professor Masamichi Yoshimura. Indeed, I have been very delighted and privileged to hear some of his very exciting and pioneering work. Professor Yoshimura is the leader of Surface Science Laboratory at Toyota Technological Institute, Nagoya in Japan, and fellow of the Surface Science Society of Japan. He's well known for his pioneering research in the field of scanning probe microscopy and nanocarbon materials. Indeed, as a world leader in surface science, he will be talking to us around what I guess this new development and this new type of materials, nanocarbons, means to the future and development of green technologies. He's, of course, very widely published and has been the president of Surface Science Society and on the editorial board of several journals. We've had the privilege of having extended discussions with Professor Yoshimura, and always Professor has amazed us with his wisdom and insights into what the future world of technology could look like. So, Professor Yoshimura.
Yeah. First of all, thank you very much for the organizers for inviting me here and so giving me a chance to talk this kind of topics. Okay, so I'm coming from the Toyota Technological Institute. What is Toyota Technological Institute? So this is located in the fourth largest city in Japan, Nagoya. So probably you know Tokyo and the Osaka. So Nagoya is in between. Okay, so it's a gravity center. Okay, and we have 2.3 million populations, and then a little bit big city, and our university. Maybe you don't know about our university. So this university is founded by Toyota Motor Corporation just 34 years ago, and this university is founded by, and the motto is here, respect the spirit of research and creativity, and always strive to stay ahead of the times. This is our motto. This is referred to Sakichi Toyota. That is the invention of the Toyota Motor Corporation. And the objective is like this, to calibrate the youth with a rich sense of humanity and creativity for innovative engineers and scientists through close collaboration with industries. Because the Toyota Motor Corporation founded our university, then we are very, very closely related with the companies in Japan. And okay, so our university is very, very small, very, very small. So the total number of students is just 500, including a PhD master student. And the faculty members is only 50. Very, very small university, just maybe just one department here. Okay, but we have always student from industry. That is our future. Our university features. Okay, and we have also collaborated with many companies. So this is this is Japanese, and this is a very, very old, little bit old data. But we have, so we have only 20 laboratories, only 20 laboratories, 20 professors, something like that. But we have many joint research with companies. Okay, yeah, that is to some sense obligations to me, professors. Okay, I'm going to talk on the scientific session. Okay, for this forum. So first, I'd like to talk on the nanocarbons. What is nanocarbons? And then I'll introduce our basic research for industrial innovation, such as a battery and a super hydrophobic and for lipophilic sponge, and also I'll talk on the artificial hip joint, which is very important in this very, very old, so old people, so many, increased in so many population of the old peoples now. And also after that, I'll show you the state-of-art nanocarbons characterization method. So probably you will be interested in this characterization method. And also, in conclusion, I'd like to talk on the future of nanocarbons. Okay, so first of all, maybe you know, I'm not sure, but 1985, the Kuroto found this kind of soccer ball molecules. This is consisting of carbons, 60 carbon atoms. This is very funny, nice structures. And after that, the Japanese professor, Iijima, he discovered this kind of carbon nanotubes. That is very nice. This is also consisting of the all carbon materials. And after that, 2004, the graphene. That's a very nice materials for the, I'll show you later. It's discovered by Novoselov in UK. And after that, the carbon nanotube, this is the carbon nanotube, and the graphite composite are also discovered by this Kondo group in Japan. Okay, so we call this one the nanocarbons families, nanocarbons, okay? And the physical properties is very, very excellent in all these graphene, carbon nanotube, and the composite materials compared with silver and copper, aluminum, whatever. Very, very great materials. Yes. And then graphene. What is graphene? Graphene is, okay, so you know, this is the black one is carbon atoms. Makes this kind of honeycomb structures. And then this is only monolayer carbon seed. And the carbon-carbon distance is very, very short. Very, very short, you know, 0.1 nanometer, something like that. Very short. But they show the great, excellent properties. For example, a higher carrier mobility is something like this. This is 10 times excellent than the conventional, you know, silicon materials. Maybe you are using everyday cell phone and a laptop. Okay, that is using silicon, but this one is 10 times higher. Okay, and also optical optical properties also very nice. But anyway, okay, so the this is the carbon nanotubes has so many applications like energy. This is the fuel cell, gas storage, and the chemistry and the composite materials. Okay, this is the reinforced materials and the nanotechnology and the electron emission, electronics. So they have many application area. Okay, for example, in Toyota Motor Corporations, we are now using this carbon nanotube as a, you know, the bumper of the car body bumper. We are using this one already. And also graphene sheet, almost the same applications are considered, but just small, okay, I can delete like this. But almost same applications are expected. Okay. So for example, FET, this is an electronic device, and the transparent films, this is, for example, a touch panel, okay, touch panel on your smartphone. And also photodetectors, and optical modulators, and then how to make graphenes. That is not so difficult. You can do it by yourself, by Scotch tape. Okay, this is Scotch tape method. Like yeah, we have many graphite, and then using Scotch tape, then we can make a one monolayer thickness seed easily. Okay, but this method is not good, valid for mass production. Then we are doing this kind of sophisticated method called chemical vapor deposition. Okay, so in this case we use the source gases like ethanol and methane, something like that. Okay, and then these gases we heat up these gases, then to dissociate to the carbon molecules like this. Then we can make a graphene, something like this. Okay, so in this case, the point is that how to make a very high quality and very, very large area graphene. That is the very important. So in this case, so we learned from the natures. This is radish, okay? So if we want to make a larger radish, then we need to reduce the seed density. Okay, probably some of you are doing this kind of plantation, I think. So in this way, we make a very big graphene. Up to now, it's a 2.5 millimeter. You can see it by eyes. Even me, or the people can see, okay? Okay, but anyway, so next I'll show you the basic research we are doing for industry innovations. So first one is lithium battery, ion batteries. So you are always using when you charge the cell phone, okay, cell phone and the laptop. Inside the laptop, there is this battery, okay? So in this case, and also in the lithium battery, we have a graphene already. And the challenge is to enhance the charge and charge properties, okay? How much charge? So now the problem is that only one day, okay? Only one day we can use for cell phone. That is because of this kind of problem we have, and how to enlarge the lifetime of the battery is that we need to know how this battery is working. That is very, very important. And for example, lithium battery need to be incorporated into these layers, but we don't know what is the path through this basal plane. This is a basal plane, or this is edge plane. We don't know. So we need to know. We need to study this behavior, to make a high performance improvement of the battery. Okay, so up to now, we are now doing, maybe you can, I'm not sure, you can see, this is the graphene layers here, and on the graphene, the second graphene, and third graphene, fourth graphene, like a pyramid. So using this kind of very, very ideal materials, we know where is the lithium is. Then we can improve the efficiency of lithium batteries. Okay, so and also I think this is very closely related with this forum, and you see we also are developing the precipitation method. That means any carbons can be converted to graphene, okay? Now how to do okay, I'll show you the method. This is very, very simple. We use only nickel. But nickel is very, very nice materials. And then put carbons, any carbons, okay, like this. Then annealing, heating, and cooling. That's it. We can make graphene layers like this through the diffusion of carbon atoms on the other side, like this. This is a very, very easy technique. And for example, so far, we successfully converted from amorphous carbon and carbon black and the adamantane polymer, something like that, to the graphene sheet like this. And also, we can now create this kind of macroscopic graphene architectures. This is a mesh, something like that, using this method. So this method is very, very cheap and very, very easy method. Okay. I'd like to talk on the other topics. This is also very important because the oil spill is now the problem, and also water is very important. The increase of the population, world population. So maybe the water is running short. So in that case, the water filtering is very, very important. To do so, we develop this kind of sponge. Okay, sponge. So probably you know this sponge. Maybe not only in Japan. Maybe you know. Yeah. So this is white sponge, melamine sponge, and then this is also very easy. Just coating of graphite oxide materials like this. This is very, very similar to graphite on the sponge. Just insert these solutions. Then we reduce using vitamin C. Okay, vitamin C probably you have in your house, vitamin C, and light you have. Okay, then reduce means to remove this oxygen from this graphite layers. Graphite itself shows very, very hydrophobic characters, very, very hydrophobic. Then if we make, so this is a product. Unfortunately, graphite is black, in color. Then the color is changed to the black from white. But anyway, so oil can go easily into this sponge. However, water still on the surface like this. Okay, so we can using this sponge, we can only pick up oils from the water like this. The surface is something like this. Okay, the surface is covered with graphene layers, which repels the water. This is a very nice materials, I guess. And also the artificial hip joint. In Japan, Japan's lifetime is very, very large, very, very long, like 85, 80, 86, 7, something like that, for the females, especially females. Okay, but we need to exchange the joint here if we want to live longer. Okay, even for the ladies, it's a very big issue now. And we have already this kind of artificial hip joint, but the lifetime is only 15 years, only 15 years. So so it's a little bit small years. Then we need to, prolong the lifetime. In that case, what is the problem is that the friction. So we have many, many frictions. If we use this hip joint, then this materials it's wasted, weird like this. That leads to the very serious diseases. Okay, So to improve these properties, we put the carbons on these surfaces like this here. This is a carbon nanotubes coated on the this biometal surfaces. So we can successfully coat it like this, and then we know that the friction behavior is very, very nice compared with the bared materials. Okay, so I'd like to talk on the nano characterization method. So this is my major. I'm getting my PhD by using this microscope, scanning probe microscope. These microscopes can see atoms, okay, very easily. For example, here, this is the, you see these spots correspond to each atoms, okay? So using these microscopes, you can see atoms as well as you can make some artificial structures like this. You see these characters, this character is Japanese. It means atoms. Atoms letters can be created by atoms, okay? Real atoms, yeah. Okay, and also fuel cell vehicle, FCV, is very, very recently released by Toyota Motor Corporations. It cost about $70,000. Okay, it's a little bit expensive, but you can buy. Maybe you can buy. Okay, the name of this car is Mirai. What is Mirai? It is Japanese. It's Japanese, but the meaning is future. So these cars only use the hydrogen. Only use hydrogen. And the hydrogen and oxygen makes just water. Water is only the exhaust on these systems. Okay, so in this case, the challenge is that how to make the hydrogen and how to dissociate hydrogen into the hydrogen atoms. This is big challenges. And okay, so in this case, the important thing is that the catalyst. So we normally use platinum. Platinum is also very, very expensive materials. Okay, so we need, and in Japan, we don't have any resources. Okay, so we need to buy from the other countries. Maybe you have here? Huh? I don't know, yeah? But anyway, so we need to know how this platinum is behaving when operating, okay? So this is very recently. I think this is last week, Toyota Motor Corporation and the JFCC. This is a kind of a national institute co-developed the operant microscope to see how this black one is a platinum, how platinum behaves when operated in this battery mode. Okay, I'm sorry, this is the movie, so you can see maybe on the website. And also here, this is the also we can manipulation technique here. So this is a carbon nanotube. Okay, this is a carbon nanotube, and the other carbon nanotube is here. So we call this one is a swordfight. Okay, swordfight. In Japanese, chambara. Okay. Oh, but anyway, so we can see each molecules, something like that. Okay, so I come to the last part of my talk. So this is the 10 most abundant element in the universe. As you see, silicon, if the silicon is 1, then the carbon is 3.5, and hydrogen 40,000. And the carbon is more very, very abundant. Okay. And already used for tire and this barbecue, okay, barbecue and the pencil, whatever, already used. And we have a natural graphite, okay, natural graphite in this Asia Pacific area, like China, Korea, Russia, Brazil is not, but anyway, Sri Lanka, and China, Korea. So there are many types of graphite here. And among these, Sri Lanka graphite is the best quality up to now. So we see this is a gravity map. You see this blue one is less gravity, and then this one, red one is a higher gravity. So Australia here, it's a little bit higher gravity, I think because of the steel. You have many steel. But you know, here, so there is India here, and here is Sri Lanka. Sri Lanka shows a very low gravity, okay? That's why elephant can live, okay? They are so heavy, but the gravity is small gravity, so they can feel very comfortable, I guess. But anyway, this year, I went down into the, this is a 500 millimeter down from the mountain. I went there to get graphite. You see, these are all graphite. So graphite is a very light material, you know, carbon, only carbon. That's why they show the very low gravities, okay? They have many other, many abundant graphite, okay? And this is an example of these materials. So this is a graphite, and the very high purity. Yeah, we already confirmed by some techniques. Okay, so up to now, we have also the waste carbon sources in addition to the natural graphite sources, natural carbons. For example, clothes, tires, woods, plant, foods, we just discard it, okay. And the gas also, CO2, many CO2, and hydrocarbons, if you burn some things. Okay, so why don't we pick up these materials to the sustainability, okay? So if we go back to our history, then so far Stone Age and Wood Age and the Iron Age, it's the 18th century, and the last century is the Silicon Age, okay? And what is next? Probably, you know. You know, yes, this is a carbon. Okay, so carbon is a very important materials, I guess, in this century, okay? And the 2050, this century, 2050, so we are now planning, in Japanese building makers, companies, trying to make here space elevator using carbon materials, because the carbon materials is very strong against the radioactive radiations. Okay, very strong. Which still is unfortunately very weak to such kind of radiations. And also we have already developed this kind of car and aircraft using carbon fibers or something like that. And of course electronics and the clothes and the daily life. So these carbons I'm sure that very, very important to our life. So that we need to use carbons efficiently. Okay. We don't use so much. We don't waste the carbon materials. Okay, thank you for your attention.
Thank you very much, Professor Yoshimura. Indeed, we've covered all of humanity's requirements, from futuristic cars to cleaning up oil spills to hip joints. So I guess you've really shed light on what the future might look like, and also importantly, how we need to be able to develop new materials which are going to allow us to sustain life as we've started to expect in terms of our standards of living, whether it's life expectancy or indeed allowing us to make more with reduced amount of resources. And it's quite exciting, and that's why I guess we are developing and looking forward to developing collaborative relationship with Professor Yoshimura in looking at how indeed we might be able to utilize a lot of these waste resources, not just in the context of recycling it in a traditional manner, but I guess effectively looking at the possibilities of transforming these waste into high performance materials. And indeed some of our collaboration and the work that we are looking at and doing so successfully right here in Australia is also how we might be able to utilize materials like waste plastics, for instance, in their transformations into nanocarbons. But the ability to be able to take that into a whole range of future possibilities is something we're really excited. And thank you, Professor, for really showing us the pathway into the future as to what green technologies and green materials may well look like into the future.